start. Pardon me. Okay. So, like I said, in a second I'm going to open the floor up to any issues or problems you guys are having with the Chapter 10 assignments. Before that, though, any questions, comments, concerns from you guys about anything else, random or on topic, before we get started with the class stuff today? That is okay. Please feel free to ask any question at absolutely any time. I'm going to load up my web assign and then have to type the password back in because, oh no, it stated I kept signed in this time. Isn't that wonderful? I'm going to load up the homework. And any questions at all about any part of the homework? I got a few questions over the weekend, so I have a couple of ideas to talk about overall. Yes?
Number 11.
11. Okay. Okay, so and the numbers up here are the randomly produced numbers for the teacher version. So everyone will have slightly different numbers. This is only the correct answer for the numbers on screen. But it'll be helpful to prove how one should get there. And I'm glad you asked about 11 because it is similar to a couple of questions on this particular assignment where we have to compare the combination of temperature, pressure, of volume, and amount of gas present in a system both before and after something changes. So, in this particular example, a person is going to inhale, take a breath, and it wasn't until I took a biophysics class at this school that I actually understood how breathing worked. Very cool application of physics. The person's chest is going to expand. That's going to change their volume. So we know the volume is going to change as the inhalation occurs. And air will flow in. Suppose the person's lungs hold at this particular moment. So this is going to be our volume initial. 1,270 milliliters. That is the volume after inhale, and the starting pressure is 1 atmosphere. If they then continue to further expand their chest cavity by a certain amount, so you know that delta V is going to be 460 milliliters, or some amount based on what your problem says, while keeping their nose and mouth closed, what will be the pressure in their lungs after this change? Assume the air temperature remains constant. So, we're given some information about our starting conditions and the state in which we are going to end. These are all of the things that begin in one mode and will change to something else as the problem goes on. The person's chest cavity is going to expand, so the volume is going to change. This is delta V, so we just have to do a tiny bit of math to find what final V is. It says the lungs expand by this much, so you take whatever your VI is and add your delta V to it. My numbers, that would be 30, 1 1 milliliters, I hope that I did that math right. And it tells us that the temperature throughout this whole process is constant. And what else will be constant throughout this whole process? What other factor affecting pressure, volume, temperature, etc. of a gas is going to be constant between once the air is in the lungs versus once they are holding their breath and then continue to expand their chest cavity? Moles, very good. The amount of gas in their lungs won't change once they stop inhaling. It says here, while keeping their nose and mouth closed so that no more air is inhaled. So, from our before state to our after state, N is also considered a constant. So the only two things that are going to be changing are pressure and volume. So, I'm going to draw your attention back to our good friend PV equals nRT. And everything on the right side of that equal sign in this question is going to remain constant throughout this whole process. So whatever N, R, and T are for this question, they aren't changing, which means if we're looking at pressure 1 and volume 1 being multiplied together, they will equal nRT. And at the same time, since these aren't changing, they'll be equal to the P2 and V2 after the change. So it's just PV equals nRT twice, kind of overlapped over each other. Because it's going to be the same nRT both times. It's going to be equal to both of them. Which means we can kind of just cut this middle part out. We only care about these numbers and how they relate to these numbers. These are constants that don't change, so you can just get rid of them. If this is equal to this and this is equal to this, then they must be equal to each other. So P1, V1 should be equal to P2, V2. And the best part of this formula is you can use any units you want with it. Because if you plug in atmospheres and milliliters on this side, you'll get atmospheres and milliliters on the other side. We were able to get to this point because PV equals nRT is kind of a combined formula. It's a combination of at least three different other formulas, which in retrospect I didn't write down for you guys, so they might not have come back to mind for you. I apologize for that. So I'm going to help rederive a few of these with you guys, the ones that will specifically be helpful on this particular assignment. So this is one of them. Absolutely have that in your notes. It should be on the class format sheet as well. PV1 equals PV2. And you can use PV equals nRT to rederive a few of these based on whatever is constant. This particular one assumes N and T are constant. We should also have, let's say for example, what I'm going to do is, real quick, I'm going to basically send the nRT over to the other side. And that'll give us PV over nRT equals 1. It's trying to seem like a weird thing to do, but that means we can set it equal to a different PV equals nRT. We can make this PV nRT1 is equals nRT2. which means you can use this if nothing stays constant. If you're comparing two direct states and nothing stays constant, you can compare the two beginning and end states like this. Just PV over nRT with all the initial states equals PV equals nRT, all the final states. You can cut the 1 in the middle out during your math if you want to. So I'm going to box this in and say asterisk if, I'm going to say only R is constant, because that's always a constant. And looking at this, we can start pulling some other things out depending on what is or isn't constant between both sides. Let's say, for example, N and V are going to be constant. Then they'll cancel on both sides, and that will leave us with P1 over T1 equals P2 over T2. Let's say pressure and moles are constant, and that leaves us with just V1 over T1 equals V2 over T2. So this is constant. N and V. This is constant. N and P. And if, say, N was the only thing constant, that would leave you with P1, V1, T1 equals P2, V2, T2. And what all of these sub-formulas can tell us is how the two individual quantities, or three individual quantities left, relate to one another after the fact. For example, here, if pressure goes up from beginning to end, volume must drop from beginning to end, because they're being multiplied together. So 1 times 1 would be the same as 2 times 1/2. So pressure and volume are inversely related, assuming everything else is constant. Pressure and temperature are directly related. 1 over 1 would equal 1 over 2. They both get, if one gets twice as big, the other would have to get twice as big. The hotter you make things, the more they move around in their container, the more the pressure goes up. Volume and temperature are also directly related if you hold pressure constant. If pressure is constant and the container has room to grow with temperature, it will. You know that about solids and liquids. And we can combine these three statements together to make this one, showing how all three of them are related, and then we have this one for how all four of them are related. Yes?
For like, can we look at the constant and then V1? Can you also do V1 over V2 equals T1 over T2?
Sorry, can you say that one more time?
So like this, the middle formula I put that where it's constant, yeah, that one.
No.
Can you do V1 over V2 is equal to T1 over T2?
You
Like
absolutely could. You
like
could reframe this as volumes over temperatures.
Because you just moved, like, I guess. Like algebraically it's correct, right?
Yes, algebraically both of these are correct. Because if you multiply both sides by T1 and then divided both sides by V2, it would end up like this.
Okay.
So
Yeah.
ultimately, these two things are the same. If you've seen them in a different form before, as long as they're algebraically connected, that is valid. The way that I've been writing them is framing things in terms of everything before versus everything after. This form is all the volumes compared versus all the temperatures compared. If that is, say, how you do it in a different class, that is perfectly valid. I don't want to force you to use my formulas. That's just how I write them. And these will come up in a few places on this particular assignment. Like, for instance, question 11. Since here we know N and T are going to be constant, we can just directly compare pressure and volume before and after. Similarly, question 10. a weather balloon has a specific radius at a specific altitude and air pressure and temperature. If the balloon is filled at, and then you're asked to compare to a different pressure and temperature, what would its radius be then? So here you're comparing the pressure, temperature, and volume in one state to the pressure, temperature, and volume in a different state. So here, for number 10, yeah, you want this one there. A couple of minor things to note: you will need to turn the radius into volume and then back, but that should be the only trick.
Would the temperature be the same though on this one?
No. It says that at its working altitude, so way up in the sky, the balloon has this radius, is at this pressure, and is at this temperature. On the ground,
Oh, I see I'm sorry, I think it's the second number.
yeah, on the ground, the pressure is instead 1 atmosphere, and that's the temperature,
I didn't know that.
which is a pretty warm day. Yes.
I don't understand the process of how to get it to the radius. Like how do you go from the volume formula?
Very good question. I'm going to go ahead and say that the formulas of geometric shapes are considered known entities, which means you can look them up whenever they come up if I fail to give them to you. I do apologize. Geometric shapes are completely fair game. The formula for the volume of a sphere is, copying this down right, 4/3 times pi times radius. It's cubed, isn't it? It's cubed. It's cubed. But because it's a known entity, you're also allowed to use calculator functions now for that one. Although, if you think about it, if you plug this in for volume on both sides, the only difference being R1 over here and R2 over here, the 4/3 and the pi would cancel on both sides. So it would just leave you with pressure 1 times radius 1 cubed over temperature 1 equals pressure 2 times radius 2 cubed over temperature 2. That'll simplify a little bit.
Wait, one more time, say that. So when you put
That's
the
okay.
volume in.
I'm going to do it over here because we're running a little out of room. Okay. Let's take PVT equals PVT. We're given our question in terms of radius and we want our answer in terms of radius. This is the formula for turning volume into radius. So let's just pop that into here so we can have all the algebra done in one swoop. Okay, so far? Now, P, R, and T are going to change from one half to the other, but 4/3 is a constant, and pi is a constant, which means they're just going to cancel on one side or the other. We could divide both sides by 4/3 and it would fall out. We could divide both sides by pi and it would fall out, which would just leave us with P1 times, and make sure you're only squaring the R1 there, over T1 plus P2 R2 over T2.
And then you can just plug in what you were doing, right?
Mhm. Yes, and again, these formulas are nice because you can put whatever you want on one side and you'll get the same thing out on the other side. The sole exception there is you still need to use kelvins for temperature. Because then suddenly this doesn't work at 0 Celsius. So. Golden rule. All normal T's must be Kelvin. Yes.
So for like number 11, like I was doing the right steps, but like the only reason why I got it, like why I didn't get it in the first place, like how do you know what is delta V versus just regular V? Like did you say that 460 was delta V?
Right.
How are we supposed to know that? Is it just reading it?
It's entirely in the wording of the question,
Yeah.
and I apologize. It gives you the initial volume. Suppose a person's lungs hold X amount of air at this pressure. If they expand their chest cavity by this amount, so this is an expansion, this is a change to this number. So that's just in the wording. Which is why step one, before even listing out your variables and your formulas, is read the question about 3 times at least. And then write down your constant, write down what you know, what you don't know, your formulas, and then read it 3 more times. I was in grad school once and I was doing a coding project, and it was only about after being frustrated at it for 3 hours, I realized I read the prompt wrong and had been doing exactly the wrong thing all day. So if A, it would never work, B, if it did work, I'd fail anyway. Which permanently enforced in my brain, read the question. Yes?
So for PV equals NRT, right, V is in liters. Or no? 'Cause
That depends on what you plug in for R. There's one R that works for liters and,
Wait, which one's the one for liters and what's in milliliters? So, oh wait. The 8.31 is for what?
8.31 is Pascal.
She said the R though, like it's for volume, it depends if it's liters or milliliters.
I thought R could go the pressure.
the different R's factor in different combinations
Oh, okay.
of what you plug in for one or the other. I apologize. Okay. R has a ton of different things it can be depending on what other units you're using. The two that we care most about are 8.314, and this is going to be for meters cubed and pascals. But if you are using liters and atmospheres, it's going to be 0.082.
Wait, did you mean milliliters?
No,
Wait,
meters.
no, for the first one.
Meters cubed and milliliters should translate.
Because they're like, 1,000.
One gram of water has a volume of 1.
Milliliter. Wait, is it gram or?
Yes.
Yeah.
The 1 liter of water has a volume of 1 kilogram. And it's 1,000 kilograms per 1 meter cubed of water.
Which
I'm psyching
means-
myself out, sorry. So when I presented this, I wrote it on the board. board instead of having it in my notes. I apologize. This is for meters cubed and pascals. This one is for liters and atmospheres. Oh yeah, look at that. Yeah, take a look here. Because the same number is presented as for liters and kilopascals, which would be the same as if it was meters cubed and normal pascals. So, now one eraser is where? And must be the way this thing's here. Okay, yes. This is the differentiation. Keeping it up here for the next day or three. Make sure that's in your notes. Because it's not in mine, and that's why I keep getting confused. So I'm going to change that real quick like.
And you said that meters cubed should translate to millimeters.
1 meter cubed is 1 meter cubed is 1 million milliliters, which means it's 1,000 meters.
Which 1,000, no. I'm just saying because for 3B, I kept putting in liters, and I kept getting it wrong, and then when I put it in milliliters, I got it right.
3. Which part, sorry?
B.
3B. Use ideal gas law to find number of moles of gas in tank. So given liters of gas, pressure in pascals, temperature in Celsius, liters and pascals. Okay, well, that's part of the problem. You don't have one R for both. Which means, yes. So as a conversion, 1 meter cubed equals 1,000 liters. The way that I remember this is, you can buy a liter of soda. It's like this. Meanwhile, 1 meter cubed of soda would be this, by this, by this. So, the trick with this question is, since it's giving you, this is number 3 on the chapter 10 homework, it gives you liters and pascals, which means that neither of these R's is completely correct. You're going to have to convert one of your 2 values into the other one. You could convert pascals to atmospheres. There is a conversion there, and I'll write it on the board in a minute so that you have it. But the easier one is meters to liters, meters cubed per liter. but for your records, 1 atmosphere equals 101,325 pascals. This is the pressure in pascals you're under at the moment.
I have a question about the grading of these. So like, for 2 of mine, there's no check mark, but like it's really close point value. So if you get one wrong more than like, I think it's 5 times, does it still give you some credit?
The machine might not give you the credit for it, but that's because, kind of like with your graphing calculator, it's real dumb. It doesn't think like I would. If you ever feel like this has to be right, if this was a human being grading this, it would be accepted as correct, and I don't want to keep spamming it and losing points to figure out what needs to change, email me. Because I can absolutely look at it, fix the score from my end of things. I just need you, your email account, to tell me which number per question it is. I will absolutely do that, but if it is in a written report, that will help me have it in my inbox and remind you to do it. So that's official policy. Please email me if the machine robs you of points that are rightfully yours.
Because like for 2 and 3, I have like 1.85 out of 2 and like 7.85 out of 8. But like there's no check marks for them, so I think like I said, I took too many tries. So like I don't know you think I didn't do them, because my answer there and I have check marks by the question, but like it's saying that like they're not like, no, that makes sense. Because like literally all the other ones have check marks, like I have full point values for those, but like for 2 and 3, I'm missing like 0.15. Which I mean is right.
If it gave you that many points, you must have, did you get all the others like on your first
Yeah.
try?
Yeah, because it was 3 and it was 2, which both had like, well 3 had the 8 part, and then 2 had 2 parts, like I said, I kept getting like stupid math stuff wrong.
Right.
But yeah, because the guy had the same thing as Excel, like 3B took me a while to figure out, because the guy kept getting like, it was slightly off, and I finally figured it out.
Right. It appears as though it doesn't give you a check mark unless it gives you the full credit. So it'll only check it if it's completely right the first time you hit enter. I've been trying to experiment with the actual assignment, the way that it is grading itself and checking that. And I need to continue tweaking it apparently, because it doesn't make that very clear to you guys, and that's not, I don't want that ambiguity on whether or not you got it right.
Wait,
So,
did you miss it more than 5?
Yeah, I think I got him like 6, and I still got, I mean, I still got some points, it just wasn't the full point value. But I got like 0.85 instead of the whole point. That's what it seemed like, because I mean, like, I thought I was gonna get 0 points for it, but I still got some credit after that.
unless, it's sounding like unless it's a red X, you have some credit for it. If it's a red X, it's 0. If it's not a red X, it is not 0, even if it's not a green check mark. But there's some settings for whether or not it confirms correct or not at certain stages. So I'm going to try to continue playing with that to make it as clear and as user-friendly as possible in terms of giving you the points reserved and making it obvious you got them. So I apologize. Today is the troubleshooting Tuesday, it seems. With the information presented today, does anyone feel like they wouldn't be able to have the assignment done tonight? Okay. So, the homework and the quiz are due at midnight, which means you have all day to continue looking at it and sending your questions and comments and concerns and valid complaints about the computer robbing you of points. And we'll make sure you get them. The quiz is also due tonight. Make sure you begin and finish that before the end of the day. I do always recommend that be the very last thing you do in the chapter. The 11 assignments are live. They're currently due for next Tuesday. And we're getting near the end of the period. I'm glad we spent a lot of time on the Chapter 10 assignment due today, but there is something that I would like you guys to at least have seen today, because it's regarding what our lab this week is about. So I want to spend at least the last couple of minutes showing you a specific formula, because it'll come up later. I guess it'll come up in lab. I will give you the mini lecture during lab to make sure you have all the things you need to be able to use that formula, but I at least want you to see it. Do a brief little foray as to what it means. So, and this is the version that I would like you to more focus on. So, right now, I just want this one. This formula here is for what we call thermal conductivity. I will write that up here. Thermal conductivity. Now, thermal energy transfers through different materials at different speeds. I want you to think to possibly even this morning. You wake up and everything in your apartment, your dorm, your house, wherever it is you're currently residing or have resided in the past, everything in your dwelling should be the same temperature, because it's been in the same temperature air all night. So every object in your room should be about whatever you say your thermostat to. Let's just say 70 Fahrenheit. But you get up and you start touching things, and they feel like they're different temperatures. You can even test this right here and now if you compare touching the surface of the table to touching the metal along the side. That's not as obvious as I'd like. Okay, if you want to, I recommend touching the surface of this granite top versus the wood of the side of it. Have you ever noticed that in the morning, that things feel like the different temperatures, even though they really should be the same? This isn't because they're at different temperatures, because they're not. They are at the same temperature. The problem is that thermal energy conducts through them at different rates, because of what they're made of and their physical construction. Again, your fingers don't have thermometers in them. They only sense thermal energy coming or going. So the hotter something feels, the faster thermal energy is entering you. And the colder something feels, the faster thermal energy leaves you. So you can touch two things at the same temperature, but if one of them siphons more thermal energy out of you because of what it's made of, it will feel colder. This formula here helps us summarize that. To briefly go over each term present, this P is thermal power. If you remember power from before, power is work over time. It is the rate at which energy is used or transferred. So this P represents the speed at which thermal energy is moving. Thermal power is the speed of the thermal energy, which means the more thermal power exiting you, the colder something will feel. So this is the speed factor here. And the rate at which thermal energy will transfer through an object depends on one second. Oh, there it is. Sorry. This is what I get for being in a hurry today. Okay. So I don't recommend crossing out the old one, but make sure this one's in your notes, because this has specific constant.
Was the other one thermal conductivity, or is this?
It was. That formula, if you want to label that formula, is thermal conductivity through multiple layers of different materials. This is thermal conductivity through one layer of one uniform material. I'm very sorry. Apparently bad things happen when I feel like I am in a hurry, so I need to take more time to zen out in the morning. I will do that for you for the benefit of the teaching. Okay, the previous formula is thermal conductivity through multiple layers of different materials. This, which is all we're going to care about for lab this week, is thermal conductivity through one layer of a uniform material. And it's the same P, it's still thermal power. This is the rate. The rate at which thermal energy transfers through anything depends on K. This constant is the part where we factor in what the object is made of. So this K is thermal conductivity constant for the material of the object. And like with every new thing, when we're talking about heat and thermo, we have different thermal conductivities for every single one. We have tables. You don't have to memorize any of them. And different materials have different conductivities. Notice, for example, metals have a lot higher thermal conductivity than, say, gases and non-metals. And when you wake up in the morning, the coldest things you typically touch in your room are probably the metals, or maybe your stone floor, depending on what dorm building you're in. Is Georgia's floor still like weird stone granite something? Okay, so that still must be awful in the morning. Meanwhile, gas is a very good thermal insulator. So even though you can go outside in the winter and you feel chilled to the bone immediately, air has a much lower thermal conductivity than, say, even waters. So if you lived underwater and it was the same temperature difference between inside and outside, you'd feel a lot worse. Or sea life. So this summarizes whatever the big thing is made of. A is the surface area that thermal energy transfers through, which is the surface area of your hand, usually. If your hand was bigger, you'd be touching more thing at once, more thermal energy would come out. With this, TH minus TC is the difference between the temperature of the hot object and the cold object. Which means that the greater the difference between the two sides, the faster the thermal energy will transfer. Thermal energy really likes to go from very hot to very cold very quickly. If the two things are basically the same temperature, thermal energy is not going to be in any hurry to finish that off. So the bigger the gap, the faster the process goes. Lastly, L is the length the thermal energy has to travel through. If you touch something with your fingertips, that length is just going to be the thickness of your skin. So that's a small number in the denominator makes the thermal transfer bigger. Meanwhile, if I say was touching the board through anything longer than my finger, now it's this length that the thermal energy has to travel through. That's going to slow the process down. I don't feel cold right now, at least not in my fingertip. The variables that make up this formula, we will be using it in lab. Sorry to keep you. We hope you all have a wonderful day. Please send me any and all questions you have on your assignments. As soon as you have them, as soon as you send the question, the sooner I can answer it. Please work together, because some of you might have to figure out one thing and others figure out different things, and teamwork makes the dream work, and have a wonderful day, et cetera, et cetera.